Well, I'm going to tell you about a formula that's emerged that we've solved, that's part of a calculation that we're doing to calculate how many primordial black holes could have formed in the early universe. Primordial black holes formed almost as soon as the universe began in many models, and they could have formed the dark matter of the universe. But we don't know how many there were, and what masses they had, and how many of a given mass there were. And so that's a calculation people try and do, and I'm trying to do it. But as part of it, this sum came up. And I looked at this sum and I thought, we have no chance of doing this sum. But actually, through a combination of high school maths, we were able to do it. So I thought it might be fun to show you. And on the way to show you some of the tools of the trade that you use when you're doing these maths calculations in theoretical physics. So the sum is the following sum. So I'll just call it I. So I is, so it's an infinite sum. The variable is n, and it runs from 1 to infinity. And in the numerator, it's n times sine of nf, and it's all divided by a thing called alpha squared, another sine, except this is sine squared now, of 2 pi n over alpha, and that's then plus pi squared n squared. And I'm interested in the limit of f going to 0. That's what I need. Alpha is just a constant, which we don't need to worry about. It tells me some information about the black holes. So this is the sum I've got. And I looked at it and I thought, I've got no chance of doing this.
So that just emerged from other work you were doing?
Yeah. This is actually, we need this in order to help us calculate a probability. And probabilities, you know, always add up to 1. You can't have more than a probability of more than 1. And to guarantee your probabilities add up to 1, you have to, we call it normalize them. And this helps normalize the probability. Now, naively, you might think this is 0 because a sine of 0 is 0. And so when f goes to 0, this sine is going to 0. But this is a bit more subtle because there are very, very large values of n in here. And so you've got a very large number times a small number, and it's quite tricky to take that limit, and this will turn out not to be 0. So what we did was, I didn't think we could do anything with it, so we just had a quick look at it on the computer. So I'll just show you what we began to see. So this is 1 over this factor I. Okay, this is prefactor we're calling it. And I did a sum, the green line, the orange line, the blue line and the red line are for different values of this upper value of n. So n of 10, n of 20, n of 50. And you see what was happening as f decreases. Remember, I need it to go down towards 0. Then say if I take the green line, this line was coming down and it seemed to be going to this constant and then it shot off. N of 20, same thing was happening, coming down to this dashed line and then it shot off. And it was shooting off earlier and earlier, but as n increased, this was staying on this constant line and then eventually going off. Remember, n really has to go to infinity. And it made me think, well, this looks like it's a number of order 6. So then I thought, okay, perhaps I can bound this. It might give me an idea of what to do. Bounding things is something we do at school. We ask, is something less than one value and is it bigger than another value? So I thought I would just do that first. So that's what I did. And the way I did it was think about the denominator. So that's this term here. So if we think about this denominator, so what is it? It's alpha squared sine squared 2 pi n over alpha plus pi squared n squared. Now this here is always positive. Everything's squared. So that means that this thing is always going to be greater than just this term by itself, right? Because, or greater than or equal to it, because if this was 0, then it would be the same. But otherwise, it's always greater, because that's always positive. But I want 1 over that. So it means that 1 over this will always be less than 1 over that. So it means that I can now say that I will always be less or equal to the sum of n equals 1 to infinity of n sine nf divided by, now I'll just include this term. I don't include that. So that's pi squared n squared. And you can see this looks, what is this actually equal to? Well, one of the n's cancels, right? So this becomes 1 over pi squared times the sum of n equals 1 to infinity of sine nf over n. Well, this looks a little bit better. Still a nightmare. We all have our tools of the trade, right? You're holding your tools of the trade. My dad was a joiner. His tools of the trade were hammers and saws. This is one of our tools of the trade. It's the book of table of integrals, series, and products. An excellent Christmas present. So in here are integrals, but there are some sums. And one of the sums, so you just get together by 1, is there. Do you see what I want? I want sine nf over n. Well, this is sine kx over k. It's exactly the same thing. So this turns out to be 1 over pi squared times by pi over 2 minus f over 2. Okay, that's what that sum is. But I'm interested in the limit of f goes to 0. And now I can take this limit. There's no n's multiplying it to cause me a problem. So it means that in the limit of f goes to 0, I must be less than or equal to, and what I have is 1 over 2 pi. That's the first. So that's an upper bound on what this sum is. And 1 over 2 pi is what? 3.14, 6.28? And that thing was...
Tau.
This is...
Yeah, okay.
Tau. Okay. Now let me try and get a lower bound. And once again, I go back to my denominator here. To get my lower bound, I can make use of the same thing. If I once again look at alpha sine squared, once again the denominator, 2 pi n over alpha plus pi squared n squared. Well, sine squared is always less than or equal to 1. Right? The sine squared function looks something like this. It starts at 0 and it will go up to 1 and then it will come down and it will go up to 1 and it will come down. So this is always less than or equal to 1, which means that this thing will always be less than or equal to alpha squared plus pi squared n squared. Because this thing's always less than or equal to 1, and that's having it equal to 1. So I can now do the same thing. I can now say that I is now greater than or equal to this sum from n is 1 to infinity of n sine nf over, and now it's this thing, alpha squared plus pi squared n squared. And so I just want to write this, if I pull this pi squared out, so this is equal to 1 over pi squared times the sum from n is 1 to infinity of n sine nf over n squared plus alpha squared over pi squared. I've just pulled the pi squared out, and so it divides that alpha squared and leaves me with an n squared. So I've got this sum. So you're going, okay, it's looking better than the original, but it's still... But I go back to my favourite book.
Your Christmas present.
Christmas present book, and I see that on the next page I have this formula. The sum of k sine kx, sum of n sine nf, over k squared plus a squared over n squared plus this thing. This is equal to a fixed function as well. It's a known function. So this actually is equal 1 over pi squared into pi over 2 times by a shine, not a sine, shine of alpha minus f alpha over pi divided by shine of alpha. So that's what this sum is equal to. Remember, I is going to be bigger than or equal to this sum, but remember I want the limit of f going to 0. So I can once again set f to 0, and can you see that I then get shine alpha divided by shine alpha, which is 1. Because it's the same thing. Sine of alpha divided by sine of alpha is the same thing. You divided sine of alpha by itself, and so it just gives me 1. So this tells me that I must be greater than or equal to, remember, I'm looking at the limit of f goes to 0. The sines cancel, and this becomes 1 over 2 pi. So I've got that I must be both less than or equal to 1 over 2 pi, and I must be greater than or equal to 1 over 2 pi. There's only one way this can be, if I equals 2 pi. So I've actually done this sum without doing this sum.
Well done.
Which means that I equals 1 over 2 pi. And so if you then go back to this prefactor, which is 1 over I, so 1 over I would be 2 pi, which would be 6.1. And that's pretty much what that is.
So for people watching, you did this sum, but this isn't the number of primordial black holes in the universe.
It's not 1 over 2 pi primordial black holes.
This is just a little tool.
It's a tool on the way. It was just an important part of a calculation which will allow us to then go and work out this probability distribution function in principle.
And how many primordial holes are there?
No.
You don't know.
I haven't been able to solve it. I haven't been able to solve the next part of it yet. Yeah, that's ongoing.
That must have been quite satisfying when that happened, eh?
Oh, it was fantastic because it never happens. Usually when you put a bound on, it'll tell you that, okay, I has got to be less than some massive number and bigger than a really small number. And you know it's a number of order, whatever, 1 over 2 pi. And you can't do that much with it. But to have it bound like that, it was just chance.
That must also give you a feeling you're on the right track.
Yeah, that's right. And so it actually made me think, okay, I'm going to try and do this. And the thing that I thought might help was so you've got this sine squared in the bottom, in the denominator here. If I first of all brought it up into the numerator, then you've got sine times sine squareds and higher order terms. And then there are things we learned at school, high school, about trigonometric identities, which I thought to myself, if I can get it so it's of the form like these, which is sine over something, and then here you've got sine over something, then I thought maybe I can then make use of these identities. But in fact, something even nicer happens, which means I didn't have to do any sums in the end. I have to write things out as sums, but I didn't actually have to do them. And we can do that if you want.
So what are you going to do now? You're going to prove something?
I'm going to prove it.
What are you going to prove?
I'm going to prove this result. I mean, at some level, I've proved it, right? I've bounded it already. And I've said it's got to, the upper bound and the lower bound are exactly the same. So it's got to be this.
Is that not enough? Why would you even prove it?
No, I was a bit nerdy. I think I just wanted to try and convince myself that I could do this because it was such a nice result. I mean, 2 pi's are... You always have a feeling you're on the right track if you've got a 2 pi hanging in there. And so that's why I then went and had another go. That's it.
The second part of this video will be posted over at Numberphile 2. There are links below, but be warned.
This gets a little bit hairy, but hang in there.
And while I'm here, can I take this opportunity to thank everyone who supports Numberphile on Patreon? It's a really important part of what we do. You make it possible for us to go the extra mile, make more videos, put more effort into them. And some of your names are here on the screen at the moment. And if you have a look down below, I will link to the full list of all our Patreon supporters. That's down in the description. Thanks a lot, everyone. We'll be back soon with another video.
Over pi squared.